Nice to meet you. This is the Hobby IT channel. Thank you for watching today. In this channel, it is a video that challenges making things with IT. Programs and circuit diagrams are available on the website below, so please make use of them. Let's have fun together.
This time, I would like to work electronically about the infrared transmission LED. We will understand the mechanism of remote control signals and modulation, and create circuits using LEDs and transistors. Next, wiring is done based on the schematic to complete the hardware. Finally, we create software to actually control home appliances. Let's start with the table of contents. Here is the table of contents. First, from the overview, we will understand LEDs and transistors. Then create the circuit and wire it. Next, we create the software and check its operation. Without further ado, I would like to move on to the next overview. This electronic work will eventually become a series of making a smart remote control, and will be distributed in a total of 7 videos. When completed, it can be operated from a smartphone, and we will realize home appliance operation from the outside and AI speaker cooperation. This is the 4th infrared transmission LED. The hardware will be completed at this 4th time. Finally, we will confirm that the remote control signal is actually sent and the home appliance is controlled. Move on. This item will be used. There is no need to use this item, but since it is an item that has been manufactured and checked for operation, please refer to the model number, etc. Please note that the price is subject to change. Also, this list can be downloaded from the Hobby IT site overview. Move on. As for the development environment, we will use Arduino. It is widely used for learning all over the world, and there are many functions such as libraries provided, and there are many learning materials on the internet. It is easy to understand and easy to use, so I will continue to use it this time. Move on. We will understand infrared transmitting LEDs. First, although infrared rays are invisible to the human eye, they are a type of electromagnetic wave, just like light. Therefore, the infrared LED also turns on and off in the same way as light. As you learned in the LED section of the previous video, you can use it in the same way as a normal LED. This time, it will be available with a forward voltage of 1.35 volts and a forward current of 100 milliamperes. As a reference, the contents of the dotted red frame are used, but there is no problem even if you use up to 1A momentarily. However, the time interval must be 100 ms or less and the duty must be 1/100th or less. I think that the duty is not satisfied, so I will consider using it as 100 milliamperes. Next, we will understand the remote control signal. The remote control signal is transmitted as a signal of 0 or 1, not that signal is 1 and no signal is 0. By changing the length of high or low of the infrared signal and transmitting it, 0 and 1 are distinguished and transmitted. There are several types, but for example, as shown in this figure, 1 is represented by making the length of low 3 times longer than that of 0. The receiving sensor was capturing the time interval between the presence and absence of this signal. However, on the transmitting side, this signal is modulated with a carrier of 38 kHz and transmitted. As shown in this figure, when there is a signal, it is not always in the signal state, but it is modulated at 38 kHz by repeating on and off every 13 ms. Since there is originally no signal when there is no signal, there is no signal regardless of the modulation. Infrared radiation itself as an electromagnetic wave has a wavelength of 940 to 950 nanometers, but the signal is transmitted by repeating on and off in units of 13 ms. As an estimate, I think that the effect is to increase the instantaneous output to extend the distance of the remote control signal, and to extend the life of the LED by making it difficult to break. Based on these, I would like to proceed to the calculation of the resistance value. As I understood in the LED version of the second video, the calculation for a normal LED is 36.5 ohms. But we did not fly as transmission distance of remote control thought. Since the LED is not always lit, but is turned on and off, consider the duty and set the average to 100 milliamperes. Since it is duty, we will calculate the ratio of on time and off time. If the on time of 1 is 3 times that of 0, and the number of bits of 0, 1 is the same, the duty is 2/3. Since this on time is modulated at 38 kHz, half of it is off time, so 1/3 of the whole on time. For this reason, in order to pass 100 milliamperes on average, it is necessary to triple the resistance value, so I set it to 10 ohms. There are many things I am still studying, including the concept of this resistance value. I would appreciate it if you could freely comment on the contents of the video, such as opinions and suggestions. Now let's move on to the transistor. As for the transistor, it has 3 terminals, as shown in the diagram here. This time it is an NPN transistor, and when a small current flows from the base to the emitter, a large current flows between the collector and the emitter. This makes it possible to control a large current with a small current. We will calculate the resistance value to be connected to the base of the transistor. The transistor this time can amplify roughly 100 times, so the resistance of the base is calculated so that the current flowing between the base and the emitter is 1/100th of the current that you want to flow between the collector and the emitter. Increase. This time, 3 LEDs transmit in 3 directions and cover a wide area, so 3 times the current is required. Also, since the resistance value is reduced to 1/3, the current will flow 3 times more instantaneously. Considering these things, it was 200 ohms when calculated as shown here. We will use this 200 ohms resistor by wiring it to the base of the transistor. Next is the circuit diagram. Here is the circuit diagram. As calculated, connect a 10 ohms resistor to the LED and use it. Also, connect a 200 ohms resistor to the base of the transistor. When IO32 of ESP32 is set to output and this terminal is turned on, a large current flows between the collector and the emitter by passing current through the base of the transistor, and the infrared transmission LED can be lit. Move on. Here is the wiring diagram. We will add from the state where the previous infrared reception sensor was wired. This is to finally complete it as a smart remote control. The wiring of the breadboard has been explained in the overview and LED editions, so I will omit it this time, but I have wired it according to the circuit diagram I mentioned earlier. Now let's wire it up on the breadboard. Here are the parts that will be wired. It's running at 3x speed. First open the bag and take out the LED. As I explained earlier, I wired up to the infrared receiving sensor in the previous video, so as a continuation of that, I will add wiring this time. This is to finally complete it as a smart remote control. The legs are a little long, so cut them with nippers. Plug in the LED. Since there are 3, we will implement all 3. 3 wires are used to cover a wide area, so there is no problem with 1 wire in one direction. Please use it by folding it in the 3 directions where the home appliances are located. Next, let's insert the transistor. Their legs are not particularly long, so they don't need to be amputated. Next, we will wire the 10 ohms resistors connected to each LED. Measure the approximate length and bend the leg. The legs are too long, so cut them off and insert them. Since there are 3, we will do the same for all 3. We will wire from 5 volts of ESP32 to the line of 24 holes on the side. Next, wire from the collector terminal of the transistor to each LED. There are also 3 of these, so similarly, measure the length, bend the legs, cut and insert. Finally, attach a 200 ohm resistor from IO32 to the base terminal of the transistor. Similarly, measure the approximate length, bend the legs, cut and insert. I've plugged it in, so I'm done. I will make software. The software used this time is posted on the Hobby IT site, so please use it. Understand the software. First, we define IO32 that controls the infrared transmission LED. Next, I pasted the remote control signal obtained and saved by the infrared receiving sensor last time. I will check the content of this signal on this slide. This information is the time with and without signal expressed in 10 microsecond units. In other words, 100 is 1 ms. There were 83 numbers in the Panasonic lighting that was carried out here. Return to program. Setup function starts. The setup function starts the serial monitor and sets the IO32 output. As explained in the circuit diagram, this IO23 controls the transmission LED by applying current to the base of the transistor. Next, the ear-send function, which performs infrared transmission processing, is executed. Here we will call the function and actually control the home appliance. Next is the loop function, but this time there is no processing. Since the remote control is only performed once at startup, processing is completed only with the setup function. Since it doesn't do anything while booting, it means there is no program. Next, let's check your send, which is a function for infrared transmission processing. As you can see here, we are declaring the variables to be used first. Next, the for statement on line 37 repeats the number of times with and without a signal. This signal will be repeated 83 times. In the for statement, there is a do while statement from line 40. This means that the do while statement will continue for the duration of with signal or without signal. Among them, only when there is a signal, the digital light on the 43rd line becomes high and lights the LED. I will confirm this line 43 on this slide. This is the program on line 43. I repeats from 0 to I count -1. It's hard to understand the contents of this control, but first of all, it is an N of I and 1. We will understand this part. Since this and processing is a bit operation, it means that it is processed in binary numbers. So, as shown here, taking the 1 in the end is irrelevant except for the last digit. Since only the last digit is relevant, since it is an AND, it will not become 1 unless both are satisfied, that is, 1 and 1 become 1. Therefore, even numbers are 0 and odd numbers are 1. In the end, even numbers are 1 and odd numbers are 0. As for the operation, if it is set to 1 with a digital light, infrared rays will be transmitted, so when I is 0, it will be 1 because it is an even number, and infrared rays will be transmitted. Also, it will be 0 when odd, so it will not be sent. In this way, high and low are alternately repeated. Return to program. The 44th line waits 13 ms. This is because it is modulated at 38 kHz, so it alternates between sending and stopping every 13 microseconds. Lines 46 and 47 are also 38 kHz modulated, so they are operating to stop transmission for 13 ms. Now, I have checked the contents of the software once. Next, we will check the operation, but first we will write this software to ESP32. If writing does not go well, you have learned about writing in detail in the LED edition, so please check the contents once. The link of the LED edition is described in the summary column. When the writing is completed, press the End button on the ESP32 to restart it. Since the state cannot be confirmed as hardware, I think that the state where the serial monitor is displayed is good. If the program is successful, it is controlling the home appliances at startup. This is what the monitor looks like. We've done this several times and it's been successful, so if it doesn't work, just to be sure, try it closer to your home appliance or try a different one. Now that I have successfully controlled the home appliance, I would like to conclude this electronic work.
We will continue to take on the challenge of making things using IT like this, so please give us a high rating and subscribe to the channel. See you next time.